Welcome in. Our goals for this video are to describe the relationships between wavelength, frequency, and energy for electromagnetic radiation. We'll use this to describe how atomic absorption and emission of light is dictated by our electrons and relate this to our Bohr model of the atom. And we'll use that Bohr model to describe our hydrogen atoms. In our previous lessons, we've examined Dalton's atomic theory, which said that everything is made out of our atoms. Later on, we learned that that was not completely true. We actually have negative electrons and positive protons, as well as some neutrons in our atom. Right now, we think about our atoms as that nuclear atom. Most of our atom is empty space. All of the mass is located in a very, very tiny nucleus in the center. The empty space is where our electrons get to live, get to hang out. As it turns out, there's a lot that we need to continue to learn about, specifically about our electrons. So far, we don't actually have a good picture about what those electrons are doing, where they are, what energies they have, what kind of shapes that they adopt. And so we're going to introduce a few theories of electrons inside of our atoms. This is going to be really useful, as it turns out the electrons are what do the chemistry that we're used to seeing in our chemical reactions. The electrons can move around to form different ions, which allows them to form ionic compounds. We can also have electrons do bond forming as, pairs of shared electrons, as we'll see in future chapters. Even just thinking about individual atoms, the electron configuration around each atom determines that atom's size, how much energy is required to remove those electrons, and how metallic those atoms might behave. So this is our goal. We're going to build up our knowledge of the electrons within our atoms in order to understand the properties of those atoms, and eventually the properties of our molecules. To accomplish those goals, we're going to have to take a few steps backwards. We're going to think about light and electromagnetic radiation. Electromagnetic radiation is a form of energy. These are beams of light that travel at the speed of light, which, as it turns out, is just a number, an extraordinarily fast number, 3 × 10⁸ meters every second that is able to travel. People have been thinking about light as a wave for a long time, and we can describe waves using a couple of properties. One thing we can do is measure the wavelength for our waves. The wavelength is defined as the distance from one peak in our wave out to the very next peak in our wave. I like to give wavelength the symbol lambda. This is the Greek letter for L. And for wavelength, we get to have units of distance. So meters or centimeters or nanometers, some unit of distance. The other main property of waves is the frequency. This is a measurement of how many waves pass by as you watch it over the course of 1 second. Imagine that you're standing here watching as this wave zips on by at the speed of light. We want to count how many of those waves are able to pass by every second that we're standing there. I like to think about this as kind of the tempo of our waves. If you've listened to music or played music, we can think about each wave passing by as maybe one beat of our music. So every time we're standing there watching it, we can make a beat every time we see one of those peaks. For frequency, I like to use this symbol. Again, this is a Greek letter. This is the Greek letter for N, called nu. It looks like a V, or I sometimes draw it as a V with some tails on each side, just so that it looks different than the V in English. There is a relationship between our frequencies and our wavelengths. If we're talking about light, it's all traveling at the same speed, at the speed of light. So, if we have something with a very compact wavelength, that means the frequency or the tempo or the beat of this wave is going to be much faster. As we're standing there watching, we can see a lot of these waves pass by every second. If you want to count a beat every time you see a wave, it's going to be a very fast beat. Meanwhile, if you have a much more spread out wave, this wave down below has a much longer wavelength. As we watch this wave pass by, it's going to have a slower beat, a lower frequency. If we count out the rhythm of this longer wavelength wave, it's going to be longer amounts of time in between those beats. This is our characteristic relationship. As the wavelength gets longer, our frequency has to get shorter. Or we can say that these are inversely proportional. They have the opposite trend. The wavelength and frequency of light also dictates how we perceive it. There are certain wavelengths that our eyeballs are able to detect. These correspond to the different colors of the rainbow. Here, if you take a beam of light and pass it through a prism, it will split up into the different colors of the rainbow. Those different colors actually have different wavelengths, and they have different frequencies. Red light has the longest wavelength in the rainbow, and violet light has the shortest wavelength in the rainbow. These glass prisms are able to split light into those component wavelengths, into those component frequencies. There's one other property of light that we can think about, and that is the energy. The energy of light actually is a little bit counterintuitive based on physics from a few hundred years ago. And actually in just the 1920s, a young Albert Einstein was able to describe the energy of our light based on its frequency. The energy of our light is exactly proportional to the frequency of that light. Or in other words, as our frequency gets smaller, that tempo gets slower, our waves have less energy. Here are all of our properties as they relate to each other. Wavelength is the opposite of both frequency and energy. As it turns out, visible light that we can see with our eyes is just one tiny slice of all the possible wavelengths and energies of light. On the left side of this image are the lowest energy waves, the ones with the lowest frequency, or the ones with the longest wavelength. On the right side of this image are waves with the highest energy, or the highest frequency, or the shortest, most compact wavelength. We have a quick practice question here. If we're thinking about different types of electromagnetic radiation, can we arrange them in order from smallest to greatest wavelength, frequency, and energy? Take a moment, grab your paper, try to find the best answers that you can. Okay, we took that step to the side to think about light and electromagnetic radiation because this is one way that we're able to study and probe the electrons in our atoms. As it turns out, electrons in our atoms can absorb some energy from the surroundings. That energy can be in the form of light, or heat, or electricity. And when our atoms do absorb that extra energy, they then try to get rid of it by emitting their own light. Here's what this looks like. You can make some gas light bulbs by trapping gas in a glass tube, connecting it to a power source, and pumping it full of electricity. Once those atoms grab that extra energy, they get rid of it in the form of light. On the left, we can see mercury is emitting light that ends up looking blue. On the right, we have some hydrogen that emits light that ends up looking red or pink. This is characteristic of our different elements. Their electrons are behaving differently, and so we end up absorbing and emitting different energies of light. Our job now is to build a model of the atom that can predict some of these properties of our atom. Can we explain why our different elements emit different colors of light? And even more confusing than this, it turns out our elements actually emit very weird arrays of light. If you look at that pink light coming out of hydrogen, it's actually not just pink light, it's exactly 4 unique energies or colors of light that are being emitted, and nothing else. We call this the emission spectrum for hydrogen. What energy of light is emitted from hydrogen? We can zoom in on this image a little bit, try to have a little bit more clarity. Hydrogen here is emitting 1 little wavelength of red light, 1 wavelength of this teal light, 1 wavelength of blue light, and 1 wavelength of purple light. Everything else is all black on the detector. No other colors of light are being emitted by this hydrogen. This has to be because of the electrons in our hydrogen. For whatever reason, the electrons in our hydrogen are leading to this pattern. This is a little bit weird and unexpected. We would expect for a light source to be able to emit every single color of the rainbow in a continuous spectrum. That is not the case, though. Hydrogen only has 4 very specific colors that it emits. Helium ends up with not 4, but maybe 5 or 6 different colors of light that are different. Neon has many colors of light that it emits, but it's not continuous. Each of our elements ends up almost having its own fingerprint of light that gets emitted when it has excess energy. To understand why this is going on, we need to introduce some of our new atomic theories with the understanding that these colors of light are because of electrons absorbing and emitting energy inside of our atom. We'll start with a simple model of the atom from Niels Bohr, developed in 1912. This is known as the Bohr model of the atom. In the Bohr model, our electrons cannot just be anywhere in the atom, in that empty space. They're only allowed in very specific orbits around that nucleus. These orbits that our electrons can exist in, they have fixed locations and fixed energies. This is what we call a quantized system. There are only specific quantities of energy that the electrons are allowed to have. This is radical and new and strange. If you're thinking about rolling a ball up and down some hills, you can roll a ball with any amount of energy. You can roll it at 1 mile an hour, 2 miles an hour, 1.15 miles an hour, anywhere in between. There's no rule that says you can't roll a ball with energy of 2.5 miles per hour or whatever. In this model, however, Niels Bohr is saying that our electrons are only allowed to have very specific energies. You can't have an electron with energy in between these two values. It can only be energy of 1 or 2 and never in between. That being said, our electrons can transition from one orbit to another, and they can do so by absorbing or emitting energy. If you have an electron with energy of 1, it's never going to be 1.5, but it can somehow jump up and absorb enough energy to get up to an energy level of 2. We can try to draw a picture of what this might look like on the right. We have our nucleus in the middle, and our electrons can exist at this n=1 orbit, or maybe it can jump up to the n=2 orbit, but you'll never find it in between those two locations. If you want to make your electron move from the first to the second orbit, you need to absorb some amount of energy. If you want to have an electron up here at the 5th energy level, it can fall down from 5 to anything lower. If you're going from high energy states to low energy states, you need to get rid of energy, emit energy. So what we're saying is we need to absorb energy to climb up to a higher level, and we get to emit or give off energy when we're falling from a high energy state to a low energy state. These circular orbits, we can picture them almost like stairs or rungs on a ladder or shelves on a bookshelf. They're at different energy levels, and so if you're trying to climb up to a higher step, you need to put energy in. If you're already at a high step and you're falling back down, that's when you get to have energy emitted. This is another way to picture this. We have here an energy diagram, an energy ladder on the left. We have low energy down at the bottom of this ladder, and we have high energy up at the top of this ladder. you can put the electrons on this ladder, on this shelf. But just like your foot on a ladder, you can't put your foot anywhere in between the rungs. You need to put your electrons exactly on one of those rungs. If you're trying to climb up to the next level, you can't stop halfway. You have to make it all the way up to at least the next rung, or you can go up to a much higher rung. But you can't stop halfway in between two of those steps. Just like climbing a ladder, getting up to these higher steps costs you energy. And when you start falling down the ladder, that's how you can get that energy back out. We've been calling these orbits by their principal quantum number. This is that letter n. We can have our orbit of 1, our orbit of 2, our orbit of 3, 4, 5, 6, and so on and so forth. This is a way to label what orbit that you're talking about. We call this as a quantum number because it can only be specific quantities. In this case, positive whole numbers. You can notice on the left, our ladder is not evenly spaced. As you get to these higher and higher orbits, they're actually closer together. Climbing from 1 up to 2 is harder to do than climbing from 5 to 6. This is literally a smaller transition to step up from 5 to 6 than it is to step up from 1 to 2. The energy level of these orbits also correlates with their physical size, the distance from the nucleus. Our higher energy orbits are bigger. Those electrons exist further away from the nucleus. All right, why do we have this theory? It's because it allows us to explain that physical property of our atoms. Hydrogen only emits red and teal and blue and purple light. But why is it only those 4 colors? And why is it nothing ever in between? Well, those emissions are going to correspond to specific movements of our electrons. In this Bohr model of the atom, our electrons can only be in certain places. And so we can only absorb or emit certain energies of light. In the Bohr model of the atom, this transition from the 3rd orbit down to the 2nd orbit corresponds to an energy of exactly red light with a wavelength of 657 nanometers. Are you ever going to have an electron move with an energy of just a little bit less? Is our electron ever going to start falling from one step to the next, but stop halfway in between? Well, the answer is no. We have to keep going until we get to the next step. That's why we only have this color, because we can only do this full step. You can't ever do a partial step. Likewise, the transition from 4 to 2 corresponds to a color of kind of this teal, blue, green. From 5 to 2 ends up emitting this blue, violet kind of color. And not pictured on this image, but you can also have a transition from 6 down to 2, which ends up being right on the edge of what we can see with our eyes, maybe around 410 for that purple transition. There we go. This is our Bohr model of the atom. We're trying to rationalize why we only see certain colors absorbed and emitted from our atoms. And we know this has to do with the electrons in those atoms. Because we only see certain colors emitted, that means our electrons are restricted in what they're allowed to do. Niels Bohr said maybe these electrons are restricted to only being in certain circular orbits. This model is incredible and matches our experimental results exactly if your atom has exactly one electron. Unfortunately, most atoms have more than one electron, and our Bohr model of the atom doesn't really have a good explanation for why this is happening. Bohr was just proposing this because it matches up very nicely with our experimental results for hydrogen. So we are going to try to do better, and in our next lesson we'll introduce quantum mechanics and a new way to picture the electrons in our atom. But for now, we've introduced light and the Bohr model, and we can at least get into this world of quantized electrons, electrons that are restricted in what energies they're able to adopt. I'll leave you with one more practice question. Here we have two different transitions in our hydrogen Bohr model atom, one from energy level 3 to energy level 2, second from energy level 2 to energy level 1. Which transition will have more energy? Which transition will have a longer wavelength? Take a moment, see if we can combine all that we've learned and get some good answers. Okay, thanks for sticking with me. By now we should be able to describe the relationship between wavelength, frequency, and energy for our electromagnetic radiation. We can describe atomic absorption and emission of light and know that it is dictated by electrons. And now we've introduced the Bohr model of the atom to describe at least our hydrogen atom.
Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.